Alrighty, for number 3 on the conservation of energy test, we have a little bit of a different circumstance where we have a cart going down a hill and it needs to go around a loop. So the first thing to notice is that the starting height is 2.3, which means that we do start with kinetic energy, with gravitational potential energy, but it's not moving at the top, which means that my kinetic energy is going to be 0. So I have gravitational potential energy, but no kinetic at the beginning. At the top of the loop, which is what we're looking at in this problem, it does have some height, so we need to make sure we account for that gravitational potential energy, and then the rest of it will be kinetic. So be careful here when you're drawing these, that the gravitational potential energy and kinetic energy at the top of the loop is equal to the starting gravitational potential energy at the very beginning. So if I want to know the speed that the cart is going to have at the top of the loop, I'm going to take this and I'm going to go ahead and write an equation for it. So I have gravitational potential energy at the beginning is going to be equal to my gravitational potential energy at the top of the loop plus the kinetic energy at the top of the loop. So we have mg, and then I'm going to use capital H to represent the very beginning height. And then we have mg, and I'm going to use a little h for the top of the loop. And then we have 1/2 my mass times velocity squared at the top of the loop. All right, so I'm going to go ahead and plug in these numbers and solve for it. One of the things I'm going to notice here is that the mass is given, but it's also, there's a mass in all of these. So it doesn't work if you're using spring potential energy, but if the mass is in every term, then you can cancel it out. On this exam, I asked you to use G as 10, so we're going to go ahead and use G as 10. Starting height was 2.3. G is 10. The height at the top of the loop is 0.62. Be careful to not use the radius there. And then plus 1/2 velocity squared. All right, so I'm going to go ahead and throw this into a calculator. So I have 23 is equal to 6.2 plus 1/2 v squared. I'm going to subtract the 6.2 to the other side. And then I moved over the 1/2 by multiplying times 2. And then I square root that to get 5.796. And I am going to use those extra numbers right now because I am going to use some of this stuff later on in the problem. All right. Then it says draw a force diagram and write the net force equations for the block at the top of the loop. Well, at the top of the loop, I know that it's going to be going really fast. So it's not going a minimum speed at the top of this loop. I know it's not a perfect circle. Just go with it. So at the top of the loop, it does have gravitational force. And I also am going to have a normal force. So if this is going really fast, the track also has to push it down towards the center of the circle. If it's going too slow, it's not going to make it around the loop. It's going to fall. And if it's going the perfect speed, it will have just gravitational force at the top. So I'm going to have gravitational force and my normal force at the top of this loop. And so the sum of my forces, I am always going to make the positive towards the center. And so I'm going to have my gravitational force plus my normal force is equal to my mass times the acceleration to go towards the center of the circle. When we're talking about acceleration to go towards the center of the circle, it's v squared over r. And gravitational force is mg. Normal force is what I'm solving for. And so I'm going to go ahead and write this out. Alrighty, so I go ahead and substitute all of those numbers in. I'm using the velocity from part A for my velocity here. And then I go ahead and solve, and I get a normal force of 157.42. And that normal force is going to be towards the center of the circle. So this is part B and C. Let me know if you have any questions.